So now we can look forward to a talk on the perspectives on the future by David Cross. And as it was already mentioned a couple of times before, everything we do here is basically based on a discovery for which David Cross got the Nobel Prize awarded for physics in 2004, together with Pulitzer and Wilczek, for the discovery of the asymptotic freedom and strong interaction. So David is now a professor at UCSB and a permanent member of the Kavli Institute. David was also in charge of this program in the past. Okay, so thank you, David.
Anyway, when Lance asked me to give something at the end of this conference, I was delighted to be back. I guess last year I somehow missed the teachers' conference, but it's great to be here. This is, I think, the 17th year, or there was some argument. 18th? So does that make it 17 or 18? Anyway, we're almost 20 years of these conferences, and they're going great. And this one has been spectacular, I'm sure. So originally I decided I would just give a, like a 15-minute talk without a presentation. But then sitting here and hearing these marvelous presentations and realizing that although Lance only gave me 15 minutes, he reserved 45 minutes for discussion. I thought I would extend and revise my remarks and build on a talk I gave at Lindau, which is where Nobel laureates meet in the summer. This was actually an anniversary meeting across all fields of science. So I talked about the future of particle physics, and I stole some of the slides during Brian's talk, which was, the last two talks I thought were absolutely spectacular. The point of view of a theorist looking towards the future and experimentalist explaining how one might actually discover new things. So that's what I'll do. And since we have all this time for discussion, please interrupt me at any point, and we can use that time during the talk. So I'd also like to go back to something I think both speakers talked about, which Rutherford's discovery of the nucleus 105 years ago, because that was the beginning of particle physics. And Rutherford, I think, invented how to probe the structure of microscopic matter. In his case, he was interested in the structure of the atom. And, microscopes then and now can't really be used. Or actually, microscopes are beginning to barely be used nowadays with modern lasers perhaps to study atoms, but at that time it was impossible. So he figured out that he would use radioactive particles, alpha nuclei, for which he won the Nobel Prize in chemistry for, to bombard gold atoms and see how they scattered, and have his, to correct Brian. Where's Brian? Somewhere. Correct Brian slightly. Marsden was an undergraduate who was doing an undergraduate project for the Rutherford, and Geiger was a postdoc. Sorry? Tom, but you talked about it, right? No, but somebody, you complained, right? That Geiger and Marsden didn't get the credit. So Rutherford, clearly thought of this experiment, set it up. The Geiger, who was a young postdoc on a visit from Germany, and Marsden, who was this undergraduate, did indeed the observation. They sat in a room for 3 hours. Their eyes got used to the dark, and then they would measure where the deflected alpha particles would hit this screen which would fluoresce. Actually, if you look at the paper which announced the measurements, Rutherford's name is not on it. He didn't actually put his name on it, even though he was the head of the laboratory and had thought of the experiment and conceptualized it. But the reason it's called the Rutherford's discovery of the nucleus was that his paper on the theoretical implications of that discovery was published right after that experimental paper on which his name did not appear. So, Rutherford was an incredible experimenter, but he was also a pretty good theorist, and he knew enough electromagnetism to calculate. I mean, he knew that electrons were charged. There had to be positive charge in the atom to neutralize it. So somehow they were deflected off the positive charge, and there was this smooth distribution of the positive charge, the so-called plum pudding model of J.J. Thomson. And an alternative, obviously, is that all the charge is localized in some point. And that's what the data that Marsden and Geiger had measured gave support to. And he calculated we call now the Rutherford cross-section. Nobody had ever calculated it before. He calculated and compared with the data, which he, before he did the calculation, he already knew somehow that the charge had to be localized, because indeed a lot of the alpha particles were coming straight back at large angles, as Tom said. And he remarked this was astounding. It was like throwing a brick at a piece of tissue paper and having the brick come back at you. You don't expect that. You expect a little deflection, but not coming back at you. And too many of these alpha particles were coming back. So he did the calculation and discovered that all the positive charge and the mass of the atom was in a nucleus that he couldn't measure the size of, but he could bound it as Tom explained. Most of what's been done at the LHC is to put bounds on various theories, speculations, and physical properties. In this case, 100,000 times smaller than the size of the atom. So that was the discovery of the nucleus, but perhaps even more importantly historically, it was the invention of particle physics. Before that, people had discovered one particle, the electron, and had absolutely no idea how to probe the structure of the atom. It was impenetrable. Well, Rutherford penetrated it with the beam of alpha particles, and we haven't really, experimental particle physics is fantastic what they can do, improving on Rutherford's method. But part of the problem we face, perhaps towards the future, is that we really haven't gone beyond this basic concept. To probe the structure of matter, you smash things together, see what comes out, and try to figure out what goes on inside the nucleus. And, we now have, you've heard much description of the accelerator and the detectors and the unimaginable marvels that our experimental colleagues can do with these machines and these detectors. It's truly amazing. One of the perspectives that one has when one is in a field like this for, I must say, going on half this period of since Rutherford, is how at any point in time what you can imagine that experimenters can accomplish 10 years or 20 years is always underestimated by a factor of 2 to 10. I mean, it's just always inconceivable. Now, since I gave this talk in Lindau, I remarked that, the incredible advances over these 105 years in our understanding of what goes on inside the atom, inside the nucleus, has been recognized by the Swedish Academy. And there are actually 52 Nobel Prize winners who, in a sense, contributed to the emergence over those 105 years of the Standard Model. So this is a quick history course of all of the Nobel Prizes that were awarded for what falls under this Standard Model theory that we have now. This is not the invention like general relativity, which is also a bit of a, it's not exactly correct to say that that's one man's invention, but the Standard Model is an example of important theories in physics being the contribution of many, many people over many, many years. There were 30 Nobel Prizes and 52 laureates, many shared, 20 in experiment and 10 in theory. This is interesting. The Swedish Academy definitely prefers experiment to theory. This ratio, 2 to 1, is not as bad as it is in cosmology, for example, where there have been many prizes recently, in the last 2 decades, for great discoveries in structure of the universe, from cosmic microwave background to the acceleration of the universe, and pretty soon to gravitational waves. But there have been, the ratio is infinite. There have only been Nobel Prizes in experiment and observation, and none in theory. But this is understandable. As Tom said, when you discover something, at least with 5 sigma, you know it's there, especially if your friends next door have verified it. But when you make a theoretical proposal, it's nature who decides whether it's there, and that takes years, and it takes the Swedes even longer. So that Standard Model did require, this is a very simple, you've seen a few times, a description of what I like to call the standard theory. A model is a bit of a, it's not respectful enough. This is the best theory one has ever had in physics, with a few parameters. 19, Brian explained, but for most purposes, for example, to calculate your mass, almost no parameters are needed. And if you want to be precise, you need 2 or 3 more. But all in all, it explains the forces and the constituents of matter, and as you've heard, and the Higgs. And it required, so where did it start? This story of the first elementary particle is J.J. Thomson, discovered the electron, cathode rays, pulled electrons out of atoms, the beginning of modern technology, as well as the understanding of the atom. Then we have Rutherford, who actually won a Nobel Prize in chemistry for radioactivity, which informed us about the nuclear force. But before he could win the Nobel Prize for the discovery of the nucleus, he died at a rather young age. Niels Bohr, within a few years, these are the dates of the Nobel Prizes. The colors are experiment, the red is theory. Niels Bohr, in 1913, 2 years after Rutherford's discovery of the nucleus, had a model of the atom which used quantum mechanics, and not only was the beginning of explaining the atom, atomic structure, molecular structure, all the normal physics, but also led to quantum mechanics. And Chadwick discovered the partner of the proton, the neutron. Anderson discovered anti-electrons, positrons, predicted by Dirac. Ernest Lawrence invented the modern way of probing matter using accelerators. Blackett also discovered in cosmic rays the pion, the muon. Yukawa, the next theorist, had a theory, applied quantum field theory, which was a rather new subject, and it had only been used at the beginning to discuss electromagnetism to try to understand the nuclear force, and predicted a particle. The pion as the carrier of the force, the nuclear force. The idea is wrong, but it played a very important role, and the pion was discovered. The thing about particle physics is it's not for nothing that it's called particle physics, because everybody is looking for a particle, and theorists get a lot of credit for predicting a particle, and experimentalists for discovering a particle. And even though Yukawa's theory wasn't very successful, he predicted a particle, which was discovered by Powell. And these, Kush and Lamb did important discoveries in quantum electrodynamics. The quantum field theory discovered discrepancies which Yang and Lee, third theorist, predicted or suggested or understood that parity was violated in the electroweak, the weak interactions. Glaser invented the bubble chamber. Hofstadter was a pioneer in electron-proton scattering experiments. Segre and Chamberlain discovered the antiproton, or confirmed the antiproton. Theorists who understood, figured out how to finally use quantum field theory successfully and for quantum electrodynamics. Louis Alvarez, who was a leader in analyzing high elementary particle collisions and discovering a whole zoo of heavy protons, hadrons. Murray Gell-Mann, who understood the symmetries of hadrons and was one of the proposers of the idea that the constituents are quarks. Richter and Ting, who discovered the J-psi particle, this is now in the 70s, and which was very important for the acceptance and understanding of quantum chromodynamics. Grashow, Salam, and Weinberg for their theory, which is now part of the standard model of the electroweak interaction. Cronin and Fitch for discovering that time reversal invariance, or CP invariance, is broken in nature. Rubia and Vandermeer for discovering or confirming the existence of the W and Z carriers of the electroweak force. Letterman, Schwartz, and Steinberger for confirming or discovering that there were different flavors of neutrinos. Friedman, Kendall, and Taylor for the modern Rutherford experiment, in which they used electrons to bombard protons and see that they were made out of point-like quarks. Charpak mostly for instrumentation, for discovering, the spark chamber, I think. Not the spark chamber, right. Rhines and Pearl for the discovery of the tau, tau meson, and the observing the neutrino. Ed Hooft and Veltman for the understanding of the electroweak theory and how to do calculations in non-abelian gauge theories. we're getting to modern times. Davis and Koshiba for neutrino oscillations and solar neutrinos. These people. Nambu and Kobayashi and Moskawa for chiral symmetry breaking, and 3 families and CP violation. These are also theorists, by the way. They should have a star. And finally, Unglair and Higgs. This talk was given before the last Nobel Prize for neutrinos. So this standard theory, which you've seen and you've had wonderful descriptions of its properties, is really a theory. And I've been lobbying for some years to change the name from model to theory. It's a theory because you can put it on a T-shirt, and you have. So this isn't an equation. This is what we call Lagrangian. So if it was a classical theory, the equations would follow by looking for the extrema, the maxima or minima of this Lagrangian. But everything is here, and just about every observation that has ever been performed, in principle, in an insanely reductionist way, could be calculated from this theory, we believe. And you've heard some of the evidence for that. And you continue to look for violations of the predictions of the theory, and you find none. There are phenomena that lie outside the theory, but theory seems pretty damn good. And if you include classical relativity, which is this term, Einsteinian terms, and the cosmological constant, you have just about all of physics. And so this is, if this isn't a theory, so model is a very bad term. Theory is unbelievably successful. And as I said, it's a culmination, well, it's not just of 105 years with those 52 people who represent a community of thousands and thousands, but it's really 2,000 years of an effort to understand matter and force. The other thing about this theory is, with theories in physics, you can take a theory and just by looking at its structure, theoretically, sort of figure out where it's going to fail. That's true for models, for explanations of certain class of phenomena. You know where it's going to fail. Electricity and magnetism had a problem from the beginning. People worried about in the 19th century that if you either say the electron is a point-like particle with electric charge, or it has structure. Now, if you say it has structure, you don't know anything about its structure, you don't have a complete theory. If you say it's point-like, however, you have a problem, because then the self-energy of a point-like particle with zero size is infinite. This was always a problem that was in the back of people's minds. And you could sort of figure out where that problem would become real, observable, and not, immediate. So, and you can do that partly on the basis of understanding the dynamics of the theory, the various phenomena, partly just dimensional arguments. If you take the standard theory and try to say, we have lots of experimental tests that it works at zeptometer, which is a milli, I like to refer to it as milli-nanometer scales. And as far as we can tell, it works to the edge of the universe. This includes all of the physics we use to explain everything in the universe, and it works. If we extrapolate that theory to where it might fail, or where it must fail, or where something is going to go wrong, until we get to the Planck length, there's no evidence that it fails. There's no place where it has to break down. That's amazing. And in a sense, it's So for somebody who's been around for a long time, it's quite amazing. Because there's no way, when I started graduate school, or got my PhD, which happens to be 50 years ago, I could imagine that we would be at this stage at this time in history. But there are problems, and some of them have been referred to. Some of them are the kinds of problems that theorists worry about. They have nothing to do. An experimenter is given this theory, measures parameters like the quark and lepton, neutrino masses and mixings. Those are measured, and then you can use the theory to calculate. So the theorists come along and say, well, the pattern of quark and lepton and neutrino masses is totally bizarre and crazy, factors of 90,000 or more if you include the neutrinos, and we should be able to calculate that. But that's just faith in how successful science has been for 2,000 years. There's nothing in the structure of the theory that says you have to be able to calculate it. But the fact that we can't, and the fact that we have no understanding of it, suggests that something is incomplete about the theory. But we always have to remember that's a very powerful statement, which I totally subscribe to, of the strength of science. We have good reasons to conjecture that science will be able to answer any question that is well posed scientifically. And if theory is unable to do so, something is missing. Then there's a parameter in QCD, called the theta angle, which is very small. We know from observation, and we don't know why. Again, we should be able to answer that. But, it doesn't hurt the theory. Then there's quantum gravity. There's a different kind of problem. Our understanding of gravity is great. It can even be able to calculate the waveform of what happens when black holes merge and send off waves we observe 1.3 billion years later. We now know. The problems there, again, are theoretical. We know that we have good reasons to believe that this part of the theory have to be altered, but they're all just theoretical clues, not direct. Then there's dark energy, which Brian said we have no understanding of. I disagree. This is a great prediction of Einstein's theory of general relativity, where there's been a lot of confusing remarks about it, but Einstein wrote down, for the wrong reasons, a form of energy which looks the same to all observers. That's pretty crazy, This table has energy. It's at rest compared to me, so its energy is mc squared. But, if I push this table and it's moving, it's got more energy. There's kinetic energy in addition. There's only one form of energy. There's only one kind of stuff that has energy and pressure that looks the same to all observers, and that's dark energy. Einstein knew that was allowed in his theory, which was based on the principle that all observers are equivalent. So if there's energy in the vacuum pervading all of space, it has to look the same to all observers. And there's only one such kind. When we observe the universe's expansion accelerating, that's a consequence of that kind of energy pervading the universe, and the fact that its equation of state, or the relation between the energy density and the pressure pervading space, is what it is one of the, in my opinion, one of the great successes of general relativity. What we don't understand is the magnitude. But that's a theoretical problem. I don't know. We should be able to calculate everything if you are a strong believer in the power of physics. But it's not a serious contradiction and it's actually a great success. Yes?
Just wondering, 10 to the 100th is not a theoretical problem.
Oh, it's a theoretical problem, but only if you believe you can calculate it. You see, unless you believe that physics has the power. So sometimes I quote Einstein's goal, which I subscribe to. Einstein said, final theory, or what we are in search of, is a theory which is so powerful, whose principles are so powerful that within this theory, all dimensionless measurable parameters should be calculable, and that any attempt to adjust any of them would destroy the theory as a whole. Now, we have a theory with 19 parameters, which we can now calculate the specific density of water when it freezes, which anthropically had better be, lighter ice than water. Otherwise, the oceans and we wouldn't be here. We already had a theory in the 20s called quantum mechanics plus Coulomb's law plus the existence of nuclei. Essentially has no parameters except for the fine structure constant, which allow us to understand atomic molecular physics, therefore biology and all of. Here we have 19 parameters. But Einstein would say, okay, these arbitrary parameters must be fixed by a better, more comprehensive theory. And the places where you might be most worried are those parameters that are abnormally large or small. Because you could imagine some kind of principle that would allow you to calculate ratios, explain why the up quark the down quark is almost twice as heavy as the up quark. But to explain why this number in natural units is, as you say, 10 to the minus 120, suggests that it's not just a simple tinkering with this structure, but a profound change. So that's the principle of naturalness. When we encounter very small numbers and measure very small numbers, we suspect that something is really wrong with our theory. But in principle, anything we can't calculate suggests that the theory is incomplete. Anyway, but more important, of course, beyond the Standard Model, as was explained beautifully by Brian, was the evidence from experiment, the existence of matter that astronomers discovered and has not been seen on Earth, neutrino masses, baryon, why are there more matter than antimatter, and indeed cosmic acceleration. But also, as Brian discussed, we have these theoretical questions. And they're based on, this ambition to explain everything, but also on the past success of physics in, for example, unifying forces. Electricity, magnetism, standard theory unifies to some extent the forces. All of these numbers we can't calculate, and so on. So you've heard a marvelous discussion of some of the outstanding. And as Brian also explained, some of these, especially the existence of dark matter, the unification of the forces, the Higgs mass, the electroweak scale, suggest have pointed to, years ago, to perhaps a single unifying explanation, a new symmetry, which is enormously, if discovered, would be enormously revolutionary, because it would tell us that space-time is not what you thought it is. It really has quantum dimensions. Supersymmetry is not just saying there's a particle for every other particle. It is a symmetry of space-time. It's an enlargement of what we think of as space-time with extra quantum dimensions, dimensions measured with numbers that don't commute when you multiply. And that would be a great revolution, not as great as perhaps some of the others we speculate about, but enormous. Space-time is our most primary concept, and if you think about it, nobody's ever observed space-time. You're so familiar with it that you think it's real. But think, what is your basis for that? If you really think about it, you'll realize space-time is a useful concept. And in fact, each of us, in what was perhaps our greatest intellectual achievement of our lifetime, on our own invented space-time when we were infants trying to get the toy on the other side of the room, absorbing all this stimuli, these photons coming in. Before our brains had fully developed, while our brains were developing, we were constructing a model of physical reality in which events and things are located in space and things change in time. But you've never seen space or time. It's a concept that we have invented, very useful for describing physical reality, and one that has been under continual attack and revision for the last 100 years, with special relativity, general relativity, now quantum dynamical space-time, string theory, and supersymmetry. And this is around the corner, which is one of the reasons it's so exciting, and the experiments at the LHC are so exciting, because they could actually discover the particles predicted by this new symmetry, eventually, with enough confirmation of those predictions, come to the conclusion that all of us will have to accept that we live in superspace. That's a better model of which we embed events in physical reality. Now, the evidence for that I'll pass over quickly because Brian and Tom both discussed it. Dark matter arises naturally in in most supersymmetric models, or attempts to enforce such symmetry on nature, and predicts a candidate and explains the abundance, crudely speaking, hasn't yet been seen. But one thing I want to suggest is that this kind of discovery of astronomers of dark matter, which we don't know what it is, but might be supersymmetry, many of us, you get the feeling if you listen to Brian or to me or to others, we take as a very important clue for supersymmetry, perhaps at the TeV energy scale that the LHC is exploring. Now, why? Well, supersymmetry is beautiful. It can explain a lot of things. It's not constructed to do so, so that makes it attractive. It might solve the abundance of dark matter problem in addition. And we have very few clues like this. High energy physics, fundamental physics of this type, where we go to the frontiers of small distances and large energies, is very clue impoverished. And therefore, there's a tendency of some of us at least I would say, very general tendency to take certain clues we get from observation very seriously. This is one of them. But we have to remember always that it could be a total coincidence. It's the nature of the field we're in. Other fields of science are awash with fuzzy clues and, imprecise experiments and lots of observations. And the art there is to pick out of all that mess, what's important. But we are faced with the opposite, a scarcity of clues. The other clue that I think was also discussed by Brian and was the unification of the forces, which as we go to high energies. Now, this is a remarkable clue. It's remarkable in many ways. One I'll come back to, which is the incredible reach of scales. I'll come back to that shortly because, in a sense, it's incredibly arrogant to even take this seriously. This is an extrapolation of theory, you see, over 15 orders of magnitude. It's only in this kind of science that we're exploring at the LHC that anybody would think of extrapolating a model, it's actually a theory, over 15 orders of magnitude. Most areas of science, nobody trusts scientists to extrapolate 1 order of magnitude, much less 15. Now, there are reasons why it's justified, but the fact that these forces come together here, and the other fact that they're all gauge theories, SU3, SU2, U1, that fit together with no missing pieces into very simple, larger gauge symmetries, suggests that there isn't much more going on until the forces are unified. As Brian suggested, it's also the place where gravity becomes strong, the famous Planck scale, which leads us to new attempts, like string theory, to unify all the forces, including gravity. Now, again, as Brian pointed out, supersymmetry helps in that unification. That extrapolation, which was done in the middle 70s, if the standard model theorists extrapolate, fails. This is the inverse coupling, which, as Brian explained, are straight lines, strong force, electromagnetism. They should meet at a point. If the theory has a common origin, if the standard theory has a... But they only do so if you add supersymmetry with a breaking at around a TV. And this, again, is an important clue for many of us for unification of all the forces and for supersymmetry at a TV, or a total coincidence. Again, these clues are essential. Nobody can directly observe what goes on at the Planck scale. But we have this extrapolation that allows us to deduce this very important clue, but it could be totally wrong. It could just be a coincidence. Many people take that clue very seriously and have. That's the reason supersymmetry so far has survived so long without any direct observational evidence. But many people are willing to give it up. There's nothing but that clue. You couldn't give it up and say it's a coincidence. And that's the nature of research in this field. It's kind of dangerous. You have to take a risk and believe things on the basis of very flimsy evidence and extrapolation. Like string theory, which I'm actually not going to discuss too much. I do want to remark about So I'm talking about perspectives, the Planck scale. So that scale where the forces, near where the forces seem to unify, is defined by, was originally defined by Max Planck back in 1899. Now, Planck, knew nothing about the Standard Model, but if you read his first papers in quantum theory, the thing he's most excited about is the realization that in addition to the velocity of light and Newton's constant that measured the strength of gravity, he had found a third dimensionful parameter. On physics, you measure everything. I'm sure you explain to your students, you have to have units. The answer is never 3, but 3 newtons or 3 pounds or whatever the physical units of the quantity you're discussing. And you need a unit of length and of time and of mass. And that's all. Every physical observable has some units, which can be expressed in terms of the basic units of length, time, and mass. But those can be replaced by other dimensionful, measurable physical quantities like the velocity of light, strength of gravity, or the quantum of Planck's quantum constant. And these, since they play such an important role in physics, the limiting velocity of light, the universal attractive force between massive or energetic objects, and the quantum of quantum mechanics, the unit of quantized packets of energy, it's natural to use these as to define natural units. So we can always redefine our units so that all of these are equal to 1, which is what we do. We measure velocities with respect to the velocity of light, and so on. They define a unit of length, 10 to the minus 33 centimeters, comparing it to the size of human feet, or 10 to the minus 43 seconds, or 10 to the 19 GeV. Now, Planck was very happy that he had these universal units. In his paper, it's interesting, he's very excited about this. He says that if we ever communicate with extraterrestrial civilizations on Sirius, and they ask us, how big are you? We would obviously say, well, we're roughly 10 to the 35 natural units. Because everybody in the universe would know that these are the obvious natural units to describe the physical world. He doesn't remark on the fact that these units are so microscopic with respect to not just the macroscopic units, but also the size of atoms or nuclei or quarks. So this is a fact of nature. And this is a fact of nature that with the discovery of the Standard Model theory and its extrapolation, we've had to live for 40 years. And it's what I call the curse of logarithms. So this physics varies logarithmically with energy. So we go back to those curves where the forces were coming together. That was over a range of energies of 10 to the 15. Those forces decreased by a factor of 2 or 3 because they vary once you get beyond the scale of atoms, logarithmically with energy. So therefore, that means that to get a big change in physics, you have to make the energy change exponentially. And so this is the size of the atom that was being probed by Rutherford. This is a logarithmic scale because things are only varying logarithmically. And this is the size characteristic size of the proton, of the strong of hadrons. This is the characteristic size of the electroweak interactions that are being probed at the LHC. And we've gone in 100 years over roughly 7 to 8 orders of magnitude. And with tests like Tom described, we've gone another factor of 1,000 beyond this. The next generation of accelerators will maybe increase the energy and decrease the length scale by a factor of 10. But the Planck scale is out here. Now, actually, on this doesn't look so bad. We've managed to go from here to here, from the size of the atom to zeptometers, or whatever they are. And gravity, is the Planck scale, unification scale is out here. It's just another, but this is a logarithmic scale. And the real problem is that dollars, the cost of these things, does not increase logarithmically with energy. It increases actually exponentially with, increases like some power of the energy or the exponential of the physics. So on the scale of dollars, we have Fermilab here, the Tevatron, and we have the LHC here, and maybe the next generation of accelerators at the very end of the scale of billions of dollars. This is 10 billion-ish dollars. But if you ask where the Planck scale is on this plot, well, let's see, it's probably in San Diego. So this is the curse of logarithms. As you go to shorter and shorter distances, things change, but they change logarithmically. But the cost of probing shorter and shorter distances, higher and higher energies, increases exponentially. These machines get bigger, the time scale gets longer, the number of collaborators required rises, and most importantly, the cost to society becomes bigger and bigger. That is, a fact of nature. And it's one that one clearly could be concerned about, especially in the long term. In the immediate future, I like to describe the situation from two extreme points of view. One is optimistic point of view, one is a pessimistic point of view. Theoretical physicists, experimental physicists tend to oscillate, sometimes within the same week, between extreme optimism and extreme pessimism. You see an anomaly out there at the tail of your experiment and well, it might be real, it might be false. It's false. You go from extreme optimism and excitement to pessimism. Same thing happens in theoretical physics all the time. But there is a phenomena in fundamental physics, this kind of physics. Most of our colleagues are optimists. That's not necessarily because they're always successful. It's because the pessimists leave the field. So I'm an optimist, but I'll start with a pessimistic scenario, which is roughly that, this is a very old slide, comparison of Higgs predicted with Higgs observed. And so far, it's held up. The Higgs boson, it used to be called the Higgs-like boson. Now I think the word like you've dropped down. It seems to be right on the nose. That's great. Triumph of theory after 50 years. But on the other hand, it doesn't teach us anything new. We knew that in a way. No signal so far for supersymmetry, no detection of dark matter anywhere, no direct indication of where there could be very high and inaccessible for generations or ever. What to do? Now, this is perfectly possible. I won't say how likely it is, but perfectly possible. Then there's the extreme optimistic. Yes, 5 minutes. The extreme optimistic scenario. The Higgs isn't exactly the standard model Higgs. It's a new way of probing new physics. Might be the case. Our colleagues will actually produce supersymmetric particles and detect dark matter everywhere. And we'll know what to do next, where to look. The Higgs has already taught us what to do next in some respect, because to truly probe that new doorway into perhaps new physics, you should study the Higgs with machines that can do better than the LHC. And there are such machines that are being discussed. But, in both cases, my conclusion is the same. We must fully explore the next range of energies. So the reason is that if you're totally pessimistic, the pessimistic scenario, this is, in a sense, incumbent on you, because you are faced with all of these mysteries and problems and issues, and you haven't gotten the information, and you can do this. So you must. In the case where there is information, of course you must, because there's a whole new world out there. And the reason you should do this is that we did it before. The machine we need is essentially the SSC, which, if it hadn't been canceled, would have discovered the Higgs and would now be in probably finished upgrade, or in the process of being upgraded to 100 trillion electron volts. Very doable. And in fact, there are plenty of suggestions for building it. And in particular, the one that excites me the most, because it's a source of new money, new involvement of a major country, now world player, is what I call the Great Collider in China, which is a Chinese proposal to build right here where the Great Wall began, a 100 DV, a two-stage collider that would extend the reach of the LHC. I don't have time to talk about the theoretical frontier into string theory and gravity. I'll just zoom through the various issues and try to end the universe. How did the universe begin? These are all actually illustrations of the incredible reach, at least if not of our understanding, of the questions we ask. So let me end with this optimism. And the reason I'm an optimist, aside from the fact that I haven't left the field yet, is that my reading of history and my own experience in science is that once a fundamental question becomes a well-formulated scientific question, so it's approachable by experiment, observation, and mathematical model. So this is once a question, this is once theorists ask new questions that are scientific in nature, and the origin of the universe is beginning, for example, to be such a question, it will be answered in your lifetime. And this is something that's unexpected because people can't see very far. The questions that were asked when I was a student were, what are all these particles, and what are they made of, and what is the proton, and why does it weigh 1 g? How can I understand the forces that act within the nuclei? And that was all answered. And just about all the questions that we were, if you had asked somebody somewhere, and you go back and look at the yearly conferences, what are the outstanding questions in particle physics 40 years ago, They've all been answered. Most of them. Or one or two. The other is experimental. Again, once an important scientific instrument is technically feasible, it tends to be, and addresses a fundamental scientific question and not just a commercial thing, because that depends on society and people and taste, and it'll be built in your lifetime. Even though it's unimaginable how they'll do it, but it will happen. So that's the reason to be an optimist in this field, even living under the curse of the logarithms. There are new discoveries potentially around the corner. There are even new tools, perhaps, to continue with Rutherford's technique of colliding particles. There are new ideas, and we have this great theory, but the questions we ask are actually much more exciting than the ones we answered and we're asking. And we have all of these opportunities around the corner. So, new experiments, new discoveries, new ideas, the best is yet to come. That was my 15 minutes.
Thank you very much for this optimistic view of the future. So maybe one or two urgent questions. I know the shuttle is waiting, but I'm sure we can manage one or two questions. Okay. Yes, it's coming.
Could you clarify your resistance to using the word model and theory? How are you parsing those two terms?
Well, so I don't like the standard model, which was, as I described to some people during the break, was invented by Steve Weinberg to describe his variant of the electroweak theory way back, and then now has come to be the term we use, because a model isn't respectful enough. A theory is a set of principles or equations, a set of parameters that you have to input, a set of rules that allow you to make predictions and to calculate and to confront experiment. That's what I call a theory. So Newton's theory of gravity was such a theory. Maxwell's theory of electromagnetism was such a theory. They explained a very small class of phenomena. The standard theory explains just about everything anyone has ever measured. And in a reductionist sense, we have no reason to suspect that it has any limitation except at these extremely short distances. So that, deserves the title theory. A model is usually a set, is an approximation based on within a theory to a set of phenomena that you'd like to understand, and you're willing to make certain assumptions and simplifying assumptions and approximations, and then you have a model. And if it fails, doesn't threaten your basic principles or basic equations, it just means you have to add something to the model. There are certain aspects of that in the standard theory. To explain, for example, massive neutrinos, you must add another Majorana, perhaps, neutrino to the game. It's a simple modification. But at its heart, this is a beautiful theory based on underlying symmetry principles and with unimaginable power. String theory is not a theory. That's why we can't test it. It's what I call a framework. Quantum field theory, which is actually, in my terminology, not a theory either. It's a framework. Quantum field theory has certain principles that can be tested, but nobody tests them. Once in a while, within quantum field theory or quantum mechanics, you have to add other ingredients to get a specific theory, like quantum chromodynamics, which is a theory. Then you can make predictions. So a theory is something in my mind which makes precise predictions, can be ruled out by experiment. A framework is a general set of principles which we've learned are often more comprehensive and more fundamental than a specific theory within that framework. And in particular, string theory, which was originally thought to be a new approach and had certain uniqueness characteristics that might pick out what would be a theory that we could compare with experiment, has turned out to be, one, a framework, and two, a framework which overlaps and is often dual to and not distinct from the same quantum field theory we use to describe the Standard Model. So in the theoretical part of fundamental physics, we're now largely, theoretically, in the business of exploring an enlarged framework that includes quantum fields and strings, all part of the bigger understanding of the framework. And we don't know what the final framework is, much less what picks out a particular theory like the standard theory. So that's my distinction between framework, theory, and model.
I think that's a good place to end the session. So please let's thank David and all the other speakers again.
Thank everyone for coming. Thank Lance for his work and Greg as well. Please be sure you leave your survey in the survey bucket right by the front door. And it is the case still that we do run this teacher in residence program. If anybody's interested and hasn't applied, please do. We'll be wrapping up the selections soon, so some of you may have missed that. Safe travels.